Alright, welcome to another exciting adventure of This Is My Physics Class. We're going to be talking about projectiles today, stuff flying through the air, and we're going to talk about some World War II stuff because I always found bombing runs fascinating. If you really understand physics, they're very interesting. That's my statement. I'm sticking with it. So we've got a bomber traveling perfectly horizontally at 160 meters per second, an altitude of 4,500 meters. How far does the bomb travel horizontally before it lands? So I know we've got a picture here, but we still want to draw our own little sketch. So I'm going to draw, oh look, it's my bomber. Yay, bomber. And it's traveling at 160 meters per second, perfectly horizontally. And it's going to drop a bomb, so it's going to fall down to the ground. And it's going to fall for 4,500 meters, and then it's going to land somewhere out here. And this is a big thing. Everyone's like, oh, it just falls straight down. No, it doesn't. It's moving, okay? So the bomb's going to still travel with the bomber for a while, and it's going to basically have that nice projectile path to it. And so we want to figure out how far does it actually travel before it lands. We're looking for that delta x. So big thing about projectile problems is you want to be able to separate your x information from your y information. So I'm going to make myself a little t-chart here. So I'm going to put all the x info and keep it separate from the y info. So in the x-plane, we're going to travel a nice constant velocity in the x-plane of 160 meters per second. And I know nothing about how far I'm going to go. I'm going to look into that. And then I know I need time because you always need time, projectile problems. In the y-plane, some of the things I know for a fact is I'm going to fall down, so I know my displacement. And since I'm falling down 4,500 meters, that's going to be a negative displacement. And then I know that I'm in free fall, so I know my acceleration is negative 9.8 meters per second squared. And then I also know, since it's perfectly horizontally, that my initial velocity in the y-plane is going to be 0. It's not at any angles, up or down. It might as well have just been dropped for all I care. So now I'm really looking for this guy right here. That's the guy I want to know, but to get that, I need to know my change in time. So that's where I'm going to be using my information from my y-plane to help me get there. All right. So I'm going to be looking for time. So all this information is going to help me out with time. So if I look down my list of kinematics equations, well, the kinematics equation that's going to help me is going to be delta y, and it might look as delta x on your sheet, but basically y is for the y-plane, equals v sub naught delta t plus 1/2 a delta t squared. So let's put in the information we know. Negative 4,500 equals 0 plus 1/2, negative 9.8. Looking for that change in time. It happens to be squared here. So when I do our math, we find out that our change in time is a whopping 30.3 seconds. So if you've got a bomb falling on you in World War II, you had about half a minute to get out of the way, I guess. Not like that would really help you. But once you have this time, now we can take that information and we can go up and look at all this X information. So I'm going to change my colors just to show the distinguish here. So now in the X plane, we're traveling at constant velocity. So the only equation we ever really use in the X plane is the one for average velocity, because average is the same as constant in a way. So this is the equation I like to use. And so we knew that our velocity was 160 meters per second. We're looking for the displacement, and now we're going to use that time that we just solved for in the y-plane, because time is the link between the two variables. So if you look, now the only thing we have to do is solve for our displacement in the x-plane. And when we do that, we get a nice little value of 4,848 meters. And so that's how far the bomb actually traveled from when it was dropped. And I find this fascinating because when I was a kid, there was a movie called The Memphis Belle, and the guy had to figure out how to put it in the pickle barrel, he said. And so he had this table of charts, and what this table of charts was basically them trying to figure out if they're traveling at a certain speed, at a certain altitude, exactly where do they need to release it, because this bomb is going to travel almost 5,000 meters, which is, I mean, if you think about it, this is the equivalent of almost 3 miles. Okay, so this bomb is going to travel horizontally about 3 miles. So they had to do a lot of math to figure out exactly where it's going to land. All right, so that's one conceptual thing. Some other conceptual questions that you should be aware of is, where's the bomb when this thing goes off? So where's the bomber when the bomb actually hits the ground? So here's the bomb, and it's going to move like this, and it will hit the ground here. Well, the bomber has the exact same horizontal velocity. So when that hits the ground, the bomber is still traveling directly above it, as long as there's no air resistance, which there is in reality, but this is the conceptual physics question. So the bomber has the exact same horizontal velocity. So it's still traveling at that 160 meters per second horizontally, just like the bomb was traveling at 160 meters per second horizontally. So they are right above each other. So that's why if you watch the old movies from World War II and any bombing runs, they'll have that picture of it just going right down the bomb bay doors, and it looks like the bombs are falling in a straight line path. That's actually why I chose this picture, because they're falling right on top of each other, but then when they hit the ground, one will hit here, the next will hit here, and the next will hit here, because they are released with certain time difference, and so that's going to represent a certain horizontal distance they're going to travel. So it'll be like boom, 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 and I'm sure one of them hit the pickle barrel. One of them got where it was supposed to go, but definitely not all of them would land the exact same spot. So that's a very interesting conceptual question, as well as with the bomber, the Enola Gay, when it had to drop the bomb on Hiroshima, it was told that when you drop this bomb, you need to bank hard, because if it did not bank hard, then that mushroom cloud would have basically gone right up there and destroyed the airplane. It'd be like, oh, look, there's a cloud coming at us, and then there wouldn't have been much reports coming back from that. So you always want to make sure that you understand that the object that's falling still has the exact same horizontal velocity as the object that dropped it. But going back to the crux of the problem, you also need to make sure that you understand that time is the thing that links the x-plane and y-planes together. And so when you're solving for these projectile problems, you pretty much always want to solve for time. Thank you, and come again.